Indirect delivery. We will continue with indirect delivery, how actually your laptop sent to your router and then sent to Converge to actually route packets. Now consider another example. Our Windows host an IP datagram to send to the host ftp.uu.net whose IPv4 address is 192.48.96.9. Figure 5.16 bottom shows the conceptual path of the datagram through 4 routers. As you can see, we have R1, which is the Converge initial router, and it also has a NAT or network address translator, which we will discuss in the future videos. Figure 5.16, direct delivery does not require the presence of a router. IP datagrams are encapsulated in a link layer frame that directly identifies the source and destination. So these IP datagrams are encapsulated in a link layer frame. So S only know this link layer, and those destination and source are always encapsulated. As you can see, we have a destination S, D as well, even in R1. Indirect delivery involves a router. Data is forwarded to the router using the router's link layer address as the destination link layer address. The router's IP address does not appear in the IP datagram unless the router itself is the source or destination, or when source routing is used. Again, the router's IP address does not appear in the IP datagram unless the router itself is the source or destination, or when source routing is used. So we only change the link layer. The SRC remain S and D. We only change the destination and SRC of the link layer. So that's the essence of that figure. First, the Windows machine searches its forwarding table, so that's your laptop, but does not find a matching prefix on the local network. So it uses its default route entry, which matches every destination but with no 1 bits at all. So the default entry, let's say it doesn't find a 1 bit in its local entry or local network, it will send it to the router. So that's how we do the indirect delivery. We send it to the router as which acts as a default route, which will now communicate to the internet. The default entry indicates that the appropriate next hop gateway is 10.0.0.1. The A side of the router R1. So this A side is actually the 10.0.0.1. Here, this is the interface of that. This is a typical scenario for a home network. Recall that in the delivery case, the source and destination IP address correspond to those associated with the source and destination host. The same is true for the lower layer, like Ethernet addresses. So in direct delivery, we point as a destination the MAC address or the layer 2. It's the same with the home address to your router, because you're essentially sending it to their MAC address or to their interface, in this case 10.0.0.1. In indirect delivery, the IP addresses correspond to the source and destination host as before, but the lower layer addresses do not. So that's the difference with indirect delivery, because you could have many routers around the route to your actual destination. So the link layer will change, but the IP, the actual source and destination, remains the same. Instead, the lower layer addresses determine which machines receive the frame containing the datagram on a per hop basis. So you see this again and again, how we go to the destination on a hop by hop basis. It makes sense that your laptop does not know where it would send, right? It makes sense to only know the nearest network where the actual destination lies. In this example, the lower layer address needed is the Ethernet address of the next hop router's R1's aside interface. The lower layer address corresponding to IPv4 address 10.0.0.1. So these are the lower layer address for its IPv4, that 10.0. So these are the MAC address, kind of like the NIC NIC interface. Now this is accomplished by ARP or a neighbor solicitation request. If this example we're using IPv6 on the networking interconnecting S and R1. So what happened is it used ARP to be able to know the nearest interface or link layer it could connect to. Once R1 respond with its side lower layer address or layer 2, S sends the datagram to R1. So it sends it via that NIC interface. It could be from wireless or direct Ethernet. I mean, usually that's wireless because it's going to the internet. Delivery from S to R1 takes place based on processing only the lower layer headers. So that's the key, it's using the lower layer headers. More specifically, the lower layer destination address. Upon receipt of the datagram, R1 checks its forwarding table. So it checks it and then we go to the next hop. So here's the example of that. Table 5.9, the forwarding table at R1 indicates that address translation should be performed for traffic. The router has a private address on one side, 10.0.0.1, and a public address on the other. So here, the R1 router has a private address of 10.0.0.1 where the source actually connect, and it actually has the B here where it has this public interface or NIC for the internet. Address translation is used to make datagrams originating on the 10.0.0/25 network appear to the internet as though they have been sent from 70.231.132.85. So it performs a NOT here to be able to convert that to a public internet. Therefore, when the public internet responds, it will go back here and it will perform a network address translation again to be sent back to the source. So basically, your home address are using IPv4, so you can think of this as the more realistic view of how it actually works in the real world, but we will also discuss that later. So your router has a one public interface and it performs NAT in each devices, just like we discussed in the previous video. It tracks what devices that sent those, and then once it received the response from the public internet, it then forward that packet to that. So the scenario, you have host S to LAN 10.0.0/25 to router R1 to internet. Now host S 10.0.0.5, for example, R1 inside interface A side 10.0.0.1, R1 outside interface 70.231.132.85. R1's default gateway ISP 70.231.159.254. So these are the basic graph of that. So the default entry indicates next hop gateway is 10.0.0.1. This is the RA. This means host has a default route in its routing table like this. So the host is, which are source or laptop, has this default routing table. Destination 0.00/0, gateway 10.0.0.1, interface ETH0. This is the RA1 interface. So when S sends a packet to any address not on its LAN, like 8.8.8, it must forward that packet to R1 at 10.0.0.1 because it's the default entry that indicates the next hop gateway. Direct versus indirect delivery. So type direct, meaning destination host is on the same link, LAN. So you don't need a router or you don't need to send anything on the internet. Lower layer, this is unusual for home address nowadays because most of us have internet. Lower layer destination, MAC of destination host. So when you're connecting inside a LAN or with no internet, you're connecting directly with the MAC. But for indirect, meaning destination host is not on the same link, it means you're connecting on the MAC of the next hop router on the internet to get to the nearest network. So in indirect delivery, the IP header's destination is still 8.8.8.8, but the Ethernet's header destination is the MAC of R1. So, like what we mentioned, the destination IP address is still the same. What changed is just the next hop Ethernet address, but the Ethernet's address destination is the MAC of R1. Fourth, it accomplished by ARP or neighbor solicitation in IPv6. Before host S can send, it must discover R1's Ethernet address, the 10.0.0.1. So IPv4 case, host S sends ARP request who has 10.0.0.1, which it founds in its default entry. R1 replies 10.0.0.1 is at AA:BB:CC. So this is the MAC address. Host S caches this in ARP table like this, 10.0.0.1 to AA, etc. So IPv6 equivalent. IPv6 has its unique IP address, so it's unlikely to still do this, NAT translation, because again, the reason why we have to perform NAT is because of limited IPv4, and most of our routers today in the Philippines still use IPv4. If IPv6, it uses neighbor solicitation advertisement, so it uses ICMP-v6 base, the classic protocol. What happened at layer 2 and 3? When S sends the packet, header Ethernet, source MAC of S, destination is MAC R1. For the header for its IP is still the same, source 10.0.0.5, destination is still 8.8.8.8. So perhaps the Ethernet changes to the next router, but the IP header stays the same, still 10.0.0.5 to 8.8.8. 6. Routers R1 forwarding table, table 5.9, destination 0.0.0, mask 0.0.0, next hop. So these are its next hop because it's the public interface 7.231. Sorry, these are the next hop, but this is the public interface 7.231.132.85. Let's check that again. Yeah. So these are the interface to the public of R1, while its next hop, or where it will send next the packet. So this is the default routing entry on its routing table. This is the next NIC where it will send the data from S that has S and D as source and destination. So destination 10.0.0.0 mask 255.255.255.128, next hop 10.0.0.100, interface 10.0.0.1. So this means for internal LAN traffic 10.0.0/25 forward directly. So that's what this table means. For everything else, default route forward to 70.231.159.254. So this is what the routing table means. So like if the router has that destination or the R1 has that destination, it will forward the traffic internally. But since it's not, it forwarded it to this 70.231.155.254 via one interface or wireless area network interface 70.231.132.85. So this interface that connects outside or connect to the internet are called the wireless area network interface. And the NAT rule means any packet leaving from 10.0.0/25 will be rewritten to appear as it came from 70.231.132.85. 7. NAT translation process. When S sends to 8.8.8.8 field IP source, before NAT 10.0.0.5, after NAT 70.231.132.85. So after the NAT, the source field will change along the internet, but the IP destination won't change. So before NAT 8.8.8, the IP destination, after NAT 8.8.8. So as we can see, the header or the part of the field of the header that changed in the IP is just the source. TCP source port, before NAT 54321, after NAT it could be rewritten along the routes or in the R1 to 30211, but it's unlikely. So TCP destination port, it's still the same before NAT 443, after NAT 443. R1 keeps a mapping in its table like so that when it receives the packet from the internet, it will be able to convert it like this. 10.0.0.5 colon 54321 to 70.231.132.85 colon 30211. It means these are the same. So it can route back the packet to the source. So when the replies come back from 8.8.8 colon 443 to 70.231.132.85 colon 30211, R1 translated back to 10.0.0.5 colon 54321. Summary of the process in human terms: host S looks up its route, sees default gateway equals to 10.0.0.1. Second, it ARPs to find 10.0.0.1's MAC. Third, it sends the Ethernet frame to that MAC. IP still destined for 8.8.8. Fourth, router R1 receives it. Fifth, R1 performs NAT, changes source to public IP. Fifth, R1, it performs its NAT and it changes its source to public IP to be able to communicate to the internet. 6. R1 forwards to ISP router. Next, hop 70.231.159.254. The process repeats until the packet reaches 8.8.8. So it also what's being done by the other router along its route. So the key idea from your code: in indirect delivery, the IP address corresponds to the source and destination host as before, but the lower layer addresses do not. So that's the core point. IP routing is end-to-end, but frame delivery is per hop. Each hop rewrites only the link layer Ethernet header, not the IP header. When R1 receives the datagram, it realized that the datagram destination IP address is not one of its own, so it forwards the datagram. Its forwarding table is searched and the default entry is used. The default entry in this case has a next hop within the ISP serving network 70.231.155.254. This is the R2 side interface. So sometimes the default entry of R1 could be another router, but in this case it's actually the actual ISP provider. We will also take a look on how do actually how that actually works in real world for ISP like Converge. So this address happens to be within SBC's DSL network called by the somewhat cumbersome name ADSL 72.231.259-254 point DSL point SNFC 21.sbcglobal.net. Because this router is in the global internet and the Windows machine source address because this router is in the global internet and the Windows machine source address is the private address 10.0.0.100, R1 performs network address translation not on the datagram to make it routable on the internet. So the router is what responsible that makes your packet routable throughout the internet. So these are the setup in real world. For example, your Converge for my Converge. So when you use Converge at home, your networks look roughly like this. For example, your laptop to Wi-Fi, to Converge ONU router, which is still private 192.168.1.1. So it ARP that first using IPv4 to be able to check this, and then this will now be converted by your actual NAT or Converge NAT gateway or CG NAT to a semi-private 10.64.x that will be used to communicate to the ISP router or outside or the core network and then to internet. So let's map to the book's example, matching the book to your setup. Textbook example, host S source 10.0.0.100. Your home network equivalent, your laptop or phone 192.168.1.10. Router R1 10.0.0.1 for its public interface. And I see. So your Converge router, its private interface is 192.168.1.1. As you can see, it's still 192.168. The same as your kinda in the same network with your laptop or phone, but they are distinguished only with one number, right? And it has its public interface of, like, for example, 100.64.x.x. Now router R2, the ISP router, converts edge router to the public internet. NAT translation from private to public. The CG NAT system Converge uses to convert from private to public. Default route 0.0.0.0/0. The gateway entry in your routing table pointing to Converge network. So the default entry or the gateway entry in our router's routing table pointing to Converge network is what we call the default route earlier, the 0.0/0. So basically the default route is anything that will be pointed to as a next hop of the Ethernet address, but the IP is still the same, the source and IP. So what actually happens in our connection when we say we open YouTube? Your laptop sends a packet from 192.168.1.10 to 142.250.190.14, YouTube's IP. The Ethernet or Wi-Fi frame is destined to your router's MAC, not directly to YouTube. So this IP will create you'll be encapsulated in an Ethernet frame destined to our router, not directly to YouTube. That's indirect delivery, exactly what the text says. Step 2, your Converge router, the R1 role, sees the packet isn't for itself. So it looks at its routing table. Default route says, send everything to the ISP gateway. So because that's the the default route, or your laptop default route, to send it to the router in case it cannot find it. Because that will be configured if you connect to your Wi-Fi via its password. So that will be automatic, being done by your OS automatically to be able to send to router via indirect delivery and then router to the ISP. So default route says send everything to the ISP gateway. Before sending, it performs not changing your IP 192.168.1.10 to its WAN address. Often something like 100.64.x.x. This is called carrier grade NAT or CG NAT. So again, before sending, it performs NAT, changing your private IP 192.168.1.10 to its WAN address so that it can communicate to the internet, so that it also can be routed back to you. So again, the one of R1 earlier, the wireless area network interface. So often something like 100.64.x.x. This is called carrier grade NAT or CG NAT. Step 3. Converge ISP router R2. It sees the packet from 100.64.x.x destined to the public internet. It forwards it using its internal routes, possibly through MPLS, like the traceroute output showed. So later we will also see how this works in actual traceroute on Windows. So the ISP will now see the packet coming from that router, from our router, that's when for public and internet. Then it will forward it using its internal routes, like its default entry, like the process repeats, possibly through MPLS, like traceroute output showed. The response from YouTube CAMBOX to 100.64.x.x, which is the converged NAT gateway. NAT gateway looks up which private IP made that request and send it back to your laptop. So that's why the router also has NAT on which device send request, because it only has one private public IP address, just like we discussed in the previous video. About traceroute and ICMP, traceroute, when you run traceroute youtube.com, you're seeing the exact path your packets take. Hop 1, your router 192.168.1. Hop 2, converge NAT gateway 100.64.x.x. Hop 3, converge core routers, global internet. This router responds using ICMP time exceeded messages, which is why traceroute uses ICMP or UDP plus ICMP. So when you use traceroute, it actually uses ICMP or UDP plus ICMP to be able to track each route. Later we will see how we were able to track each route. So how NAT and IPv6 fit in? The book explains how NAT hides private addresses, which is what your converged router and CGNAT do. If you were on IPv6, NAT wouldn't usually be needed. Instead, your device would get a globally unique IPv6 address directly from Converge. IPv6 uses neighbor solicitation instead of ARP, and ICMPv6 for path checks. So yes, so here we use a trace route because we're using an IPv4, but for ICMP or IPv6, we will have to use the ICMPv6 to check each path. So yes, this is exactly what happens on your Converge 9. Your router is doing what R1 did in the example. Converge Network Edge is doing what R2 did. NAT is happening before your packets reach the wider internet. You can verify this by checking your WAN IP in your router admin page. It will likely start with 100.64.xx, not your public IP from websites like whatismyip.com. So our one IP is different. That's our public IP. This happens to be within SBLC's DSL network called by the somewhat cumbersome ADSL 20.731.159.254. I think we discussed it. Because this router is in the global internet and the Windows machine source address is the private address 10.0.100, R1 performs network address translation on the datagram to make it routable on the internet. The NAT operation results in datagram having new source address 70.231.132.85, which corresponds to R1's B-side interface. Networks that do not use private addressing, like ISP and larger enterprises, avoid the step and original source address remains unchanged. So it makes sense that ISP that doesn't use this IPv4 or doesn't need this NAT would directly send it instead of performing that address translation. NAT is described in more detail in chapter 7. So here's the diagram. So when router R2 inside the ISP receive datagram, it goes through the same step through the local R1 did except for NAT operation. So it does the same thing that R1 did. It copies the source and destination, except it doesn't need to do the address translation because it can do it directly, like because it doesn't, it's a public IP already, and it's not. So if the datagram is not destined for one of its own IP addresses, the datagram is forwarded in indirect delivery in the nearest network. In this case, the router usually has not only a default route but several others depending on its connectivity to the rest of the internet and its own policies. So it doesn't have just one default route that has one bit, it could have also another route that has the same one bit for several others depending on its configuration to the rest of the internet and its own local policies. Note that IPv6 forwarding varies only slightly from conventional IPv4 forwarding. Aside from the large addresses, IPv6 uses a slightly different mechanism, neighbor solicitation messages, to ascertain the lower layer address of its next hop. It is described in more detail in Chapter 8 as it's part of ICMPv6. In addition, IPv6 has both linked local address and global addresses, see Chapter 2. While global addresses behave like regular IP addresses, linked local addresses can be used only on the same link. So if you use a linked local addresses, it needs to be on the same LAN. In addition, because all the linked local addresses share the same IPv6 prefix like FE80::/10, a multi-host may require user input to determine which interface to use when sending a datagram destined for a linked local destination. So because if you're sending an IPv6 to a same LAN, you need to also specify in your input what actual interface, what MAC interface are you trying to send it to. So that's usually time consuming. That's why for this it's also this process has been automated by the router as well. So to illustrate the use of linked local addresses, we start with Windows XP machine, assuming IPv6 is enabled and operational. Like this ping6, FE80, etc. Pinging no route to destination, specify correct scope ID or use -s to specify source address. When we do that again with %6 at the end, pinging FE, etc. from with 32 bytes of data, reply from bytes 32 times 1 milliseconds, etc. Ping statistics for the FE80 packets, send equals to 4, receive 4, loss equals to 0, 0% loss, approximate round trip, times in milliseconds, minimum equals to 1 millisecond, maximum equals 1 millisecond, average 1 millisecond. Here we see that failing to specify which interface to use for outbound linked local traffic results in an error because again you need an input In Windows XP, we can specify either a scope ID or a source address. In this example, we specify the scope ID as an interface number using the %6 extension to the destination address. This informs the system to use interface number 6 as the correct interface when sending the ping traffic. So how does all of this connect? Previously, we saw host S to router R1 communication, where R1 is the default gateway for a LAN, and R1 performs NOT before forwarding to the internet. Now, this new passage shows what happened after that. When host S to host router R1 to ISP R2 to internet hubs to destination, it expands the chain beyond R1, showing how forwarding, NAT, and path tracing work together in IPv4 and IPv6. So here, we see the actual real-world example beyond this R1. It shows the how forwarding the NAT the ISP interconnects step by step. What happens at R1? R1's logic: when R1 receives a datagram from the local LAN, destination is NAT itself, not 10.0.0.1. So it looks up its routing table. So it checks itself. It's not meant for itself, so that it checks its routing table. It finds the default route. Next hop is 70.231.159.254, because again, R1 could have multiple interface that could be the destination as well of the source. So as you can see, the next hop or the default route is the R ISP, which is the router 2. So R1 forwards the packet to R2. But first, NOT, it performs translation because the packet came from a private IP. So before it sent that to the default route, it performed NOT because it came from an IP. So you can kind of think the if-else statement that if it's a private IP that is not routable on the internet, R1 must rewrite the source address to public IP 70.231.132.85. This ensures that replies from the internet can come back to R1, which then translate them back to the original host. Third, when the packet reaches R2 inside ISP, R2 performs the same forwarding step as R1, except it doesn't perform NOT. So it forwards the datagram as well, same as R1, but it just doesn't do the NOT since it's already in the global internet. We're already using a public IP address, so we only perform NOT for private IP address or for home networks, or for one that use an IPv4. If it's IPv6, that's a different story as well. So it's just based on its global routing table. BGP, so which is our Converge, that's what we do with Converge or in the Philippines. The router just bases it on the global routing table BGP. Each router along the path looks at the destination IP and uses its forwarding table to send packet closer to the destination. So each router along the path looks at the destination IP. So it forward the datagram to the using the global routing table to the nearest router near the destination, and then each router along the path, as it sends the datagram, looks at the destination IP and uses their forwarding table to send the packet closer to the destination. So how IPv6 fit in? The passage says IPv6 forwarding varies only slightly from IPv4. That's because IPv6 routers still forward based on longest prefix match in their routing tables. So it also used this longest prefix match. which I think we have discussed already, in the previous video. An algorithm that allow us to do a bitwise end to from the destination and the mask to be able to get to the nearest address. So IPv6 use that as well. The difference is that IPv6 replace ARP, neighbor discovery, ARP with neighbor discovery ICMPv6 messages. So instead of ARPing to find the nearest MAC, or to find the MAC, to find the router that has that MAC in your default entry, it uses the neighbor discovery. IPv6 has linked local FE80::/10 and global addresses. So that's the only difference with IPv4. So in IPv6, each router still forward based on the destination IP. It still need to find the next hop MAC address, but now via ICMPv6 neighbor solicitation instead of ARP. Fifth, IPv6 link local address and scope IDs. The ping6 example shows that local addresses FE, AD, etc. only exist within one link, one LAN segment. You must specify which interface to use because FE80::1 could exist on multiple network interfaces or multiple NICs. That's why Windows and Linux need you to write ping6, FE80, etc. %6. The %6 does the system use interface index 6. So this part illustrates scoping in IPv6. Link local is not equal global. 6. The traceroute example. So these are the traceroute example. Now we shift from forwarding theory to observing it in action. Traceroute or traceroute on Windows reveal each router hop a packet traverses. So how? Mechanisms. It sends UDP datagram with increasing TTL values, kind of like in the IP header we discussed in the previous video. When a router receives a datagram with TTL equals to 0, it discards it and sends back an ICMP time exceeded message because it gets the hop it was allocated to. So it means it's not valid anymore. Each ICMP reveals only one hop along the path. So this is also how it calculated, or it tracks each hop because it used TTL. So once the TTL exceed, that's the time you can see the number of hop it actually took to get into the destination. So traceroute collects TTL equals to 1, R1 10.0.1, TTL equals to 2, R2 70.231.159.254, TTL3 equals to R3, ISP core, etc. until it reaches the final destination. This shows the forwarding path through the internet. MPLS and traceroute. This part, MPLS label equal 32307, COS equals to 5, TTL equals to 1, S equals to 0. Means that some routers along the path use MPLS, multi-protocol label switching, internally instead of pure IP forwarding. So someone along the path of our sending our packet along the internet, some routers will use this instead of the forwarding the datagram, which in this case its property will change compared to the normal forwarding we discussed earlier. So MPLS assign labels like 32307 to packets for fast switching. Each label can also have a class of service. COS equals to 5. TTL equals to 1 means this was the first MPLS hop. S equals 0 means it's not the bottom of the MPLS label stock. So this label info shows that ICMP time exceeded message can carry MPLS info, letting traceroute see inside those ISP tunnels. So this means that when you use a traceroute in Windows, it also shows this unique configuration of router it have to get into the destination, which kind of great because you're able to see it in details how some router actually able to configure how to process those packet than normal forwarding of datagram for indirect delivery routers. So how disconnect the NOT forwarding in ICMPv6 concept, forwarding table, description. Used by routers R1, R2 to find next hop connection. Same process for IPv4 and IPv6. So for forwarding table, or the one used by routers R1 to find the next hop, they have the same process for IPv4 and IPv6. Not description rewrites private to public addresses at R1. Connection required for private LANs to reach internet. Neighbor discovery /ARP description resolves MAC of next hop. So it's same with IPv4 and IPv6. They have the same purpose of resolving MAC of next hop. Connection happens per hop. ICMPv6 description used for error discovery like no route, time exceeded. Connection, it replaces ARP and ICMPv4 because for ICMPv4 you actually need to ping it or to use it manually. Trace route concept description uses ICMP to measure each hop. Connection, it shows how routers forward packets. So it uses ICMP, the trace route. YouTube, it actually uses to measure each hop, and along with TTL, it shows how router forward packets, or all the router it hops along the destination. MPLS description underlying ISP forwarding tech or technology. Connection invisible to IP unless ICMP reveals it via trace route. So it all connects as one consistent forwarding pipeline. You have an app connected to IP layer 3 to next hop MAC, L2 to router NAT /FIB to ICMP feedback to next hop. In short, R1 does NAT and forwards to R2. R2 and other routers forward based on global routing tables. IPv6 work the same but uses ICMPv6 for neighbor discovery and has scope addresses. Traceroute uses TTL. ICMP time exceeded to expose the chain of routers. MPLS may appear in traceroute as label info inside ICMP replies. So to see the path taken to an IP destination, we can use the traceroute program called tracecert on Windows, which is a slightly different set of options with the -n option to not convert IP address to names. So here Linux traceroute -n ftp.uu.net. We can see we have 30 hop max, 38 box packet. We also see MPLS, or some router use this special MPLS. So this program lists each of the IP hops traversed while sending a series of datagram to destination ftp.uu.net 192.48.96.9. The traceroute program uses a combination of UDP datagram with increasing TTL over time and ICMP message used to detect each hop when the UDP datagram expire. To accomplish this task, 3 UDP packets are sent each TTL value, providing 3 round-trip measurement to each hop. Traditionally, traceroute has carried only IP information. But here, we also see the following line. MPLS label equal 32307, COS equals to 5, TTL equals to 1, S equals 0. This indicates that multi-protocol label switching, RFC 031, is being used on the path and the label ID is 32307. Class of services 5, TTLS1, and the message is not the bottom of the MPLS label stock, S equals to 0, CRFC 4950. MPLS is a form of link layer network capable of carrying multiple network layer protocols. Its interaction with ICMP is described in RFC 4950, and its handling of IPv4 packets containing options is described in RFC 6178. Many network operators use it for traffic engineering purposes. So these are actually used for traffic engineering purposes, the MPLS, controlling where network traffic flows through their network. So your your setup Converge 1299. So when you use Converge at home, your networks looks roughly like this. You have a laptop or phone connected to Wi-Fi, then your Wi-Fi connect to Converge ONU/router like 192.168.1.1 private. Then it is connected to converged NAT gateway slash CGNAT, or the 100.64.x.x semi-private. Then it is connected to ISP router slash core network to internet. Now let's map this to the book example. So these are the more realistic example on the real world. Textbook example, host S, source 10.0.0.100, your home network equivalent, your laptop slash phone 192.168.1.10, router R1 10.0.0.12, 70.231, etc. 0.85. Your home network equivalent, your converged router 192.168.1.12, 100.64.x.x. Router R2, ISP router, your home network equivalent, converged edge router to the public internet. NAT translation, private to public, your home network equivalent, the CGNAT system converge uses. Default route 0.0.0/0, your home network equivalent, the gateway entry in your router's routing table pointing to converged network. What actually happens in your connection? Step 1. You open, say, YouTube. Your laptop sends a packet from 192.168.1.10 to 142.250.190.14, YouTube's IP. The Ethernet or Wi-Fi frame is destined to your router's MAC, not directly to YouTube. That's indirect delivery, exactly what the text says. Step 2. Your converged router, the R1 role. It sees the packet isn't for itself, so it looks at its routing table. Default route says send everything to the ISP gateway. Before sending, it performs NAT, changing your private IP 192.168.1.10 to its WAN address, often something like 100.64.x.x. This is called carrier grade NAT or CGNAT. Step 3. Converge ISP router R2. It sees the packet from 100.64.x.x destined for the public internet. It forwards it using internal routes, possibly through MPLS like the traceroute output showed. Step 4. The response from YouTube comes back to 100.64.x.x. It converged NAT gateway. NAT gateway looks up which private IP made that request and send it back to your laptop. About traceroute and ICMP, when you run tracecert youtube.com, you're seeing the exact path your packets take. Hop 1, your router 192.168.1. Hop 2, converged NAT gateway 100.64.x.x. Hop 3, converged core routers global internet. This router responds using ICMP time exceeded messages, which is why traceroute uses ICMP or UDP plus ICMP. How NAT and IPv6 fit in? So the book explains how NAT hides private addresses, which is what your converged router and CGNAT do. If you were on IPv6, NAT wouldn't usually be needed. Instead, your device would get a globally unique IPv6 address directly from Converge. IPv6 uses neighbor solicitation instead of ARP and ICMPv6 per path checks. So yes, this is exactly what happens on your Converge line. Your router is doing what R1 did in the example. Converge router edge is doing what R2 did. NAT is happening before your packets reach the wider internet. You can verify this by checking your WAN IP in your router admin package. It will likely start with 100.64.x.x, not your public IP, from website like whatismyip.com. So discussion. In the example we have just seen, there are a few key points that should be kept in mind regarding the operation of unicast forwarding. First, most of the hosts and routers in this example used a default route consisting of a single forwarding table entry of this form: mask 0, destination 0, next hop, some IP address. Indeed, most hosts and most routers at the edge of the internet can use a default route for everything other than destinations on local networks because there's only one interface available that provides connectivity to the rest of the internet. So most hosts use a default route because most hosts and most routers at the edge of the internet can use a default route for everything other than the destination on local networks. because there's only one interface available that provides connectivity to the rest of the internet, which in this case the actual public interface uh, of your home network. So that's the key principle. The source and destination IP address in the datagram never change once in the regular internet. So like what we mentioned, this is always the case unless either the source routing is used or when other functions such as NOT as in the example are encountered along the data path. Forwarding decisions at the IP layer are based on the destination address. A different lower layer header is used on each link that uses addressing, and the lower layer destination address, if present, always contains the lower layer address of the next hop. Therefore, lower layer headers routinely change as the datagram is moved along each path toward its destination, which confirm that the per hop MAC is always changing. In our example, both Ethernet LANs encapsulated a link layer header containing the next hop Ethernet address, but the DSL link did not. Lower layer link addresses are normally obtained using ARP, see Chapter 4 for IPv4, and ICMPv6 neighbor discovery for IPv6, see Chapter 8. Now we will discuss firewalls, some of the introduction of firewalls and network address translation. By the late 1980s and especially the early to mid 1990s, the internet had gained the interest of the mass population and ultimately people interested in compromising its security. Successful attacks became commonplace and many problems were caused by bugs or unplanned protocol operating in the software implementation of internet host. Because some sites had a large number of end systems with various versions of operating system software, it became very difficult for system administrator to ensure that all various bugs in these end systems had been fixed. Furthermore, for obsolete systems, this task was but impossible. Fixing the problem would have required a way to control the internet traffic to which the end hosts were exposed. Today, this is provided by firewall, a type of router that restricts the type of traffic it forwards. As firewalls were being deployed to protect enterprises, another problem was becoming important. The number of available IPv4 address was diminishing with the threat of exhaustion. Something would have to be done with the way addresses were allocated and used. One of the most important mechanisms developed to deal with this, aside from IPv6, is called network address translation. With NAT, internet address need not be globally unique, and as a consequence, they can be reused in different parts of the internet called address realms. Allowing the same address to be used in multiple realms greatly eased the problem of address exhaustion. As we shall see, NAT can also be synergetically combined with firewalls to produce combination devices that have become the most popular types of routers used to connect end users, including home networks and small enterprises to the internet. We shall now explore both firewalls and NATs in further detail. So we have discussed the NAT. They are used to convert or to solve the address exhaustion problem, and along with the firewall, they are actually combined to secure networks because as the internet were developed back days, there's a lot of different operating system that could be um, targeted or by bad actors. So firewalls, given the enormous management problem associated with trying to keep end system software up to date and bug free, the focus of resisting attacks has expanded from securing end system to restricting the internet traffic allowed to flow to end systems by filtering out some traffic using firewalls. So again, given the enormous management problem associated with trying to keep end system software up to date and bug free, the focus of resisting attacks expanded from securing system to restricting the internet traffic. So you're not just securing the all the host within your network, but you're also now restricting, creating a kind of like an access control of traffic of the packet that is allowed in your network, or sometimes it is being done in application level, not just in packet or layer 3. So from securing and to restricting the internet allowed to flow end-to-end systems by filtering out some traffic using firewalls. The two major types of firewalls commonly used include proxy firewalls and packet filtering firewalls. The main difference between them is the layer in the protocol stack at which they operate, and consequently the way IP addresses and port numbers are used. The packet filtering firewall is an internet router that drops datagram that failed to meet specific criteria. The proxy firewall operates as a multi-home server host from the viewpoint of an internet client. That is, the endpoint of TCP and UDP transport associations. It does not typically route IP datagrams at the IP protocol layer. So it doesn't care with the IP datagrams. Step 1, what you already know, saw from traceroute. In your traceroute, packets goes through multiple routes. Your PC 192.168.1x, home router 192.168.1.1, converged edge 10.56.0.1, converged core routers 168.49.x.x, Google 142.x.x. Each router, home, ISP or Google, looks only at IP header, source or destination, IP, TTL, etc. Sometimes transport header, TCP or UDP port if it's doing NAT or filtering. Router decide where to forward or where to drop packets. That's what packet filtering firewalls do too. They act like routers that filter. So we already actually know or somehow know how to implement firewalls using our routers we discussed earlier. So step 2, how firewalls fit into this flow. You can think of your packets journey like this. App or browser or game, layer 7, to TCP or UDP socket open, layer 4, to IP header built, TTL checksum, then which is layer 3, then Ethernet or Wi-Fi frame, then packet filters and firewalls. So this is where the packet filters and firewall lies. And then 2 ISP routers to internet to destination. Now, depending on where the filtering happens, type of firewall, packet filtering firewall, layer 3 to 4, IP, TCP or UDP, where it acts, usually built into routers like converged NAT gateway. How it connects to your trace, filter packets based on IP, port, protocol like drop port 23 or allow TCP 443. Type of firewall, proxy firewall, layer 7, application, where it acts like a middleman app proxy server. How it connects to your trace, it doesn't forward that IP layer, it terminates and recreates TCP connections at the application layer like web proxies, content filters. You can actually do this in your browser by having a proxy. You can also do that I believe in settings on your phone to be able to have kind of like upper layer application proxy created by your mobile phone operating system, which use Linux. So your converged NAT gateway 10.56.0.1 is not just routing, it's also doing NAT translation, acting as a packet filtering firewall. That's the packet filtering the text means. It sits at the same level as routers and NAT devices. Step 3, how NAT and packet filtering are connected. So in your trace route, hop 2 colon 10.56.0.1, that's a carrier grade NAT, CG NAT device. It does two things. First, NAT translation. It maps your IP, private IP to public, and then it also do the packet filtering or the firewall. It drops or allow packet based on its policy. Both are layer 3 to 4 operations, so that device behave exactly like packet filtering firewall in the book. In contrast, a proxy firewall would terminate your TCP connection. For example, a corporate web proxy that says connecting to youtube.com on your behalf It doesn't forward packets, it opens a new connection outward. Step 4. How this look like in the real world? Your Converge setup device, your laptop, Windows Defender Firewall. Function, it filters inbound connection. Types of firewall, packet filtering, layer 3 to 4. So Windows Defender Firewall is actually layer 3 or 4 to 4. Home router 192.168.1.1 function, NAT, firewall, port blocking. Type of firewall, packet filtering, layer 3 to 4. Converge CG NAT gateway 10.56.0.1 function, NAT plus ISP security policy. Type of firewall, packet filtering, layer 3 to 4. Converge corporate proxy only if enterprise. Function, traffic monitoring or URL control. Type of firewall, proxy, layer 7. Device, YouTube Edge, Google. Function, reverse proxy / CDN front end. Type of firewall, proxy firewall, layer 7. Step 5. How IPv6 ties in from your earlier question. If your Converge connection used IPv6, NAT would usually be unnecessary. Each device gets its own global IP, but IPv6 routers can still use firewall rules, packet filtering to block ports, filter ICMPv6 types, allow specific inbound flows. So again, NAT is not being done in IPv6, but they can still use a firewall to block ports, filter ICMPv6 type, allow specific inbound flows. So whether it's IPv4 or IPv6, packet filtering logic lives at layer 3 to 4. Step 6. How this connect conceptually to your textbook. Textbook concept, router R1 performing NAT. Real world example, your home router or Converge CG NAT device. Textbook concept, indirect delivery. Real world example, your packet hopping through Converge and Google routers. Textbook concept, firewall filtering datagrams. Real world example, Converge routers dropping certain packets or ports. Textbook concept, proxy firewall endpoint. Real world example, YouTube's front end reverse proxy or corporate content filter. Textbook concept, IPv6 neighbor solicitation. Real world example, would replace ARP in the same routing process. Textbook concept, trace route hops. Real world example, routers responding to ICMP at each filtered step. In short, your trace route showed routers and NAT in action layer 3 routing. The textbook section on firewalls describe how the same routers can also filter packets. Packet filtering firewalls equal operate with routers layer 3 to 4. Proxy firewalls operate instead of routers layer 7. So your Converge network uses packet filtering firewalls built into NAT routers, not proxy firewalls. That's why your packet hop through addresses like 10.56.0.1, 161.49.xx instead of being terminated by a proxy. Packet filtering firewalls. So packet filtering firewalls access internet routers filter. It drops some traffic. They can generally be configured to discard or forward packets whose headers meet or fail to meet certain criteria called filters. So that's the key, header and filter. It reject that based on that header only or the filters. Simple filters include comparison on various parts of the network layer or transport layer headers. So for a simple filter, it could just confirm various part of the layer 3 header and layer 4 header. The most popular filters involve undesired IP addresses or options, type of ICMP message, and various UDP or TCP services based on the port numbers contained in each packet. As we shall see, the simplest packet filtering firewalls are stateless, whereas the more sophisticated ones are stateful. So what are stateless and stateful? Stateless packet filtering firewalls treat each datagram individually, where stateful firewalls are able to associate packet with each previously observed packets or packets that arrive in the future to make inferences about datagrams or streams. So a stateful firewall is kind of like a stateful component in React. It is able to cache the previous state or life cycle, or the stateful in so anything stateful basically is smart. It's able to remember the previous transaction, kind of like the smart in about phase, where it remembers your previous interest, or the smart in a sense of a TLB, where it remembers the frequently used, or a spatial and temporal locality. So that's kind of smart or stateful we're talking about here. So whereas stateful firewalls are able to associate packets with other previously observed packets or packets that arrive in the future to make inferences about datagrams or streams, either those belonging to a single transport associations, or those IP data fragments that constitute an IP datagram. See chapter 10. So it's also like multi-level feedback queue, where it remembers the history and execute based on that past history. IP fragmentation can significantly complicate a firewall's job, and stateless packet filtering firewalls are easily confused by fragments. So this implementation that makes it sophisticated is because it is related to fragments. So this filter with each packet can easily be confused with that. That's why it's hard to implement. A typical packet filtering firewall is shown in figure 7.1. Here the firewall is an internet router with 3 network interfaces, an inside, an outside, and a third DMZ interface. The DMZ subnet provides access to an extranet, or DMZ, where servers are deployed for internet users to access Network administrator install filters or access control list, ACLs, basically policy list, indicating what type of packets to discard or forward in the firewall. Typically, these filters conservatively block traffic from the outside that may be harmful, and liberally allow traffic to travel from inside to outside. So for outgoing rules, most are allowed. I mean, you can be wild for that, but for incoming rules, most are not allowed. For example, we only allow TCP, UDP, or ICMP, such DNS, reply traffic, and DMZ traffic. So figure 7.1, a typical packet filtering firewall configuration. The firewall acts as an IP router between an inside and an outside network, and sometimes a third DMZ or extranet network, allowing only certain traffic to pass through it. A common configuration allows all traffic to pass from inside to outside, but only a small subset of traffic to pass in the reverse direction. When a DMZ is used, only certain services are permitted to be accessed from the internet. Proxy firewalls. Other types of firewalls called proxy firewalls are not really internet routers in the true sense. Instead, they are essentially hosts running one or more application layer gateways, ALGs, hosts with more than one network interface that relay traffic of certain types between one connection or association and another at the application layer. They do not typically perform IP providing as routers do, although more sophisticated proxy firewalls are now available that combine various functions.